Okay. So I briefly review what we learned in the previous class. So actually in the previous class, we learned about the out-of-order processor architecture. So actually GPU is the parallel processor architecture. So then I also mentioned that in the previous class, GPU architecture of the GPU is similar to the statically controlled pipeline architecture, which means that it's similar to the static pipeline architecture. But I hope you can understand some basic, the baseline ideas on the dynamically scheduled pipeline. Also, it's very important. And then also, I hope you can understand the pros and cons of the out-of-order process architecture. And then also you need to think that why GPU use the statically controlled pipeline architecture. So actually, why computer architect developed the out-of-order process architecture? So I need to know that. So in order to improve the performance of the processor, there are several different ways. But when we focus on the performance of a single core processor architecture, then we need to increase the number of instructions. So it's called the instruction level pluralism. So actually, the out-of-order processor architecture was developed for increasing number of concurrent instructions. So it's actually very important idea in the computer architecture field. So actually, so which means that we need to know. So we need to select the available instructions. So which means that the operands are ready. So if we cannot find any available instructions in a single thread, then we can select some additional instructions in the other thread. So it's the simultaneous multi-threading. It's called the multi-threading. Okay. Yeah, it's a hardware multi-threading. So we also learned about the hardware multi-threading, and then there are two different kinds of hardware multi-threading. So I hope you can understand how multi-threading is implemented in your processor. So actually, Intel or AMD processor supports the simultaneous multi-threading. So which means that we can also Intel and AMD processor support the superscalar. So superscalar means that single core can fetch multiple instructions every clock. So which means that single core has multiple slots for multiple instructions. And then actually the modern processors, which means the modern CPUs, use the superscalar architecture, out-of-order processing, speculative execution, and multi-thread. Some cores some cores support the multi-threading, and some cores do not support multi-threading. So the recent Intel architecture has the performance cores and efficient cores. And then the efficient core means that it's the power efficient core. So which means the performance is a little bit low, but it's power efficient. So it has the simpler architecture. But performance core is as you know, a performance core is focused on the high performance, which means that these techniques, so like the superscalar and then out-of-order also speculative executions, and then multi-threading is applied to the performance core of the Intel Android. So this is the some CPU's method that use the multi-threading, which means that if you can fetch any available instructions from multiple threads, okay? This is the simultaneous multi-threading. Also, there are two different ways of having a multi-threading. So coarse-grained multi-threading and a fine-grained multi-threading. Okay, a fine-grained, coarse-grained multi-threading. So as you can see, you can find the instruction frames in the multiple thread is thread A, B, C, D. And then coarse-grained multi-threading means that if a thread encounters cache miss, so you know if a thread encounters cache miss, then the requested data should be fetched from the low-level cache or even the main memory, and then it will take 100 cycles if the data is fetched from main memory. So which means that even though we use the out-of-order processing or speculative execution and then some other techniques such as the memory disambiguation, so actually the out-of-order processor, modern out-of-order processor architecture employs the many speculative execution techniques. Okay, but even though we use so many different kinds of speculative applications, if a thread encounters cache miss, then this thread cannot give available instructions for processors, which means that so usually we write the code. So if we use some variables in our code, and then we know that these variables are dependent on each other. Like A equal 1, B equal 2, and then C equal A plus B, and something like that. So every variables is dependent on each other. So the problem is that if a thread encounters cache miss, you cannot find available instructions in the thread. So coarse-grained multi-threading means that when a thread encounters cache miss and CPU performance, CPU changes, the CPU select the other thread, and then this event is called context switch. Okay, the context switch I also mentioned in the previous class. But fine-grained multi-threading means that a processor changes the executed thread every clock. Okay, like this. So then what is the advantage of a fine-grained multi-threading? So in the previous class, I mentioned that GPUs use fine-grained multi-threading. Then what is the benefit of a fine-grained multi-threading compared to the coarse-grained multi-threading? Actually, the simultaneous multi-threading is very complex. So, the GPU, actually GPU employs the static pipeline architecture because of power issue. So, the GPU is a power-hungry device. We already know the GPU. Currently, GPU consumes very much power, but if we just focus on the performance per power, GPU is more efficient than CPU. So actually, GPU architecture focused on the power consumption aspects of processor. So think like this. So there are three types of hardware multi-threading, but you cannot use the simultaneous multi-threading for GPU because it's very power hungry. So then we can compare the coarse-grained multi-threading and fine-grained multi-threading. So what are pros and cons of is coarse-grained or fine-grained multi-threading? So as I mentioned, in the coarse-grained multi-threading, if a thread encounters cache miss, and then I already explained that this thread cannot find any available instructions if a thread encounters cache miss. So then we can select the some other thread. But with the coarse grained multi-threading, you cannot hide some clock waste between the other instructions. So what does that mean? So let us assume that this is the floating point add, and then this is the another floating point mul. So floating point multiplication, and let us assume that these instructions are dependent, which means that the floating point multiplication requires the data from floating point add. So what's the problem? The latency of the floating point execution is lower than the latency of the impedance instruction. So it can take 5 or 6 clocks for executing floating point operation. So this is the 5 or clock cycles between the floating point add and the floating point execution. So with the coarse grained multi-threading, I mentioned that the coarse grained multi-threading, the thread context switch is performed when a thread converts load instruction, and then the event of load instruction is cache miss. But how about this? You cannot actually with the coarse grained multi-threading, cannot find available instructions that can deal between this floating point add, floating point multiplication. So it will take 5 or 6 cycles between these instructions, but a processor may not find any available instructions, even though the out of the processing is applied. That is the disadvantage of coarse grained multi-threading. Then, why do you use fine grained multi-threading? So, in the fine grained multi-threading, the thread executions are switching every clock cycle. So, which means even though this is the floating point add, and then the following instruction requires data from the floating point add, then we can find all available instructions between this floating point add and then floating point multiplication. So if this latency is around the 5 or 6 cycles, we can view any available instructions from other thread. That is the advantage of fine grained multi-threading. And then I mentioned that GPUs employ fine grained multi-threading because of this issue. So the GPUs. So actually in this class we will learn about the brief architecture of GPU architecture. So why do you use a GPU? For parallel processing. But for parallel processing, actually GPU has the integer and then floating point core. So actually the NVIDIA core, this is a core, but it's very similar to the ALU or CPU. But no, GPU supports the parallel processing. So and then also we use GPU for very massive parallel floating point operation. So actually, a GPU has the integer pipeline and then floating point pipeline. It's the ALU and then floating point ALU. So if GPU executes the floating point instruction, so actually GPU kernels can have many floating point instructions. Then, if we GPU the coarse grained multi-threading, then the floating point instruction is executed, then this thread cannot find any available instruction. That is the problem of coarse grained multi-threading. But if you use the fine grained multi-threading, so if this thread is blocked by floating point instruction, then GPUs can find any available instructions from other thread. So GPU, that's why GPU employ the fine-grained multithreading. So with the fine-grained multithreading, GPUs can hide some clock cycles or executing floating point instruction, or also some other complex instructions such as the special function instruction. Okay. So actually, I believe we can learn about the CPN of the CPU, this class and then the next class. But so we can, with the fine-grained multithreading, GPUs can hide tens of cycles, okay, around tens of cycles. Then what is the disadvantage of fine-grained multithreading? We cannot handle memory instructions, you know. So in the coarse-grained multithreading, if thread encounters a load instruction for example, then it's cache miss. Then we can this processor can find any available instructions from other thread. But how about the GPU? So actually, GPU each thread, it's not thread actually, but you know the GPU each thread of the GPU executes the same instruction. So which means the thread has the same structurable instruction. So let us assume that this black thread A encounters cache miss. So which means then we can GPU performs the context switch into the thread B, but with a high probability, thread B also performs the load instruction because GPU executes the same instruction. So let us assume that this thread A encounters cache miss, then thread B also encounters cache miss again and again. So let's count this advantage of fine-grained multithreading, and then also with some performance bottleneck of GPU. So which means that with the fine-grained multithreading, it's not easy. It's not easy to hide the low latency of load instruction. Which means it's a cache miss. Okay. So you need to think about some pros and cons of this hardware multithreading of GPU and GPU. Okay. And then now, so I will briefly explain about the GPU. Either I upload this slide. Sorry about that. I forgot uploading slide that. Sorry about that. So I actually, so I briefly explain and then during the break time, I will upload the slide deck. Okay. So let us compare the GPU and GPU. So as you can see, this is the NVIDIA processor, it's a very high performance server processor, and then this is the NVIDIA Tesla. It's a somewhat old generation GPU. Okay. So Intel Xeon processor is the host processor. So which means that it's a main processor that runs operating system and any other general purpose application, general purpose CPU application. And then, you know, it's NVIDIA Tesla. NVIDIA Tesla GPU is the actually co-processor. So, which means that the general purpose application, like the normal CPU application, run under this Intel Xeon processor, but actually we use GPU for the graphics application, but recently we use GPUs for parallel applications. So which means that GPU is the co-processor. So which means if the parallel execution part are executed by some GPU code, then this code is delivered to the GPU, the co-processor, and then only this part is formed by GPU. Okay, so actually, so in this class, I also explain about some GPU kernel. Okay, so but you need to remember that GPU is just a co-processor. So which means specific part of code or specific functions are executed by NVIDIA GPU, the server GPU, the general purpose GPU. Okay, so it's just a co-processor. And then how many cores? Intel Xeon processor have tens of cores. So usually 10 to 30 cores. But if we just focus on the GPU, a single GPU have hundreds to thousands of cores, and then recently reached thousands to then 10K cores. Okay, so actually GPUs have many cores, but as I mentioned, actually this core is called the CUDA core by NVIDIA. Okay, but actually its core is very similar to the ALU of CPU. Actually, the CUDA core looks like this. It's a pipeline, and then this is the integer part, integer execution unit, and then this is the floating point execution unit, and that's it. So this is the GPU core. So if you just see this GPU core, it's just two ALUs, the ALU and then floating point ALU. But NVIDIA cores, this is a core, okay? Because different threads are assigned to different ALU. That's why NVIDIA core is a core. Okay, so GPUs, a single GPU has 100,000 to 10K cores. The number of cores is very large, and GPUs focus on latency of a single thread. If we just focus on the performance of a single thread, performance is better for CPU, but GPU focused on the throughput of many threads. So targets are different. So Intel CPU is focused on the latency. So it's the performance of a single thread, but GPUs focus on throughput. Okay, it's different. So that's why GPUs are called the parallel processor. And then last of control. I said that the normal CPU application have many branches, which means CPUs have many control instructions. Actually, in order to increase the performance of a single thread, then CPUs need to accelerate this control part. Okay, so which means that if our general purpose processor, general purpose applications have many control instructions, CPUs can efficiently execute this control instruction. But few or no control for GPU. So you can say that, oh, you can use some if then else statement in GPU kernel. And that's right. GPUs also supports the some control instruction, but actually inside of the GPU architecture is not good for the control instructions. Actually, it's very efficient. So which means if we use many if then has state one to the kernel, then performance of kernel will be evaluated. So even though the control instructions are supported, GPUs have some architectural. GPUs do not have some architectural ideas such as speculative execution, branch prediction, branch target. GPUs does not have any components like this. So GPUs can support control instructions, but very limitedly. Okay. So you can just that. Then how can you implement the GPU architecture? So we can start from the existing processor. So I also explained about the display taxonomy in the previous class. So we can classify some types of processors with the type of input instruction streams and then type of data streams, like the single instruction and the single data is actually the CPU model, and the single instruction multiple data is called the CMD, and then multiple instruction multiple data means the it's called the MIMD, but it's multi-core architecture. Okay, so how a general processor supports parallel execution. So parallel execution means that, so actually the CPU, the single core CPUs exploits the instruction level parallelism, and then which means that each instruction handles the scalar data. So which means a single instruction handles single data. Okay. So which means that in order to increase the performance, then we need to increase the number of instructions. Then how can you support the parallel processing? If we increase the number of data, so I said it's a number, so actually it's the amount of data, but if we increase the number of data elements like here, then we can increase the performance, because many data are executed concurrently. But if this data is handled by independent instruction, actually this is the MIMD model. Okay. Then how can you increase the number of data? MIMD with the same instruction, and then if the same instruction, then multiple data can be processed. This is the MIMD model. So in the MIMD model, we can increase the number of data elements executed by a single instruction. So this is the parallel processing, and then actually this model can be applied. So with the MIMD model, then we can increase the throughput. Okay. So actually, if data, so actually this data is handled by a single instruction, and then this data stream include the multiple elements, and then we call this type of data is the vector type data. So I think everyone knows about the vector. So if we say the vector, then vector has many elements. Then many elements, we can also apply some vector operations such as the vector adder and the vector multiply, like like this. So it's similar to the column and row and column multiplication. So we already know there are some different operations, and then if computer instructions handle the type data, then we can increase the throughput, which means we can support parallel processing. Then how can we implement this SIMD type processor? Actually, in the CPU also, our mobile CPUs have a SIMD engine, like in the SSE or Neon engine, the SIMD engine. Actually, the existing CPU already supports the SIMD architecture. Then how can we implement this SIMD architecture? So there are two different types. So vector processor and then array processors. So actually, the vector processors were firstly developed. So vector processor means that with a vector processor, actually a single instruction like the load.3 or add.3 just the vector operand like B1, B2, like B1, B2, B3. Then how can we execute this type of instruction? So vector type processor means that actually the vector type processor has the one execution engine, and then with the pipelining, this execution engine executes the different element in a vector type data every clock. So which means that in the first clock is add engine, the vector add engine just to execute the add B1 as the element 1, and then the next clock is add E2 and E3. So you can say, what is the benefit of this vector processor? So actually the vector processor has only one execution engine, and then actually elements are executed, only one elements are executed every clock. What a benefit. But I said the vector processors are firstly developed, so which means that in that time, so actually we can include some very small amount of other resources in our processors. That's why the vector processors were firstly developed. So what benefit of a vector processor is that its instruction support the simpler time data execution path. Data execution behaviors are very simple. So what does that mean? So something like this is add x1, x2, x3, so add x4, x1, x2. So it's a two different adds. Then what is the problem with this add? We can find the data dependencies from x1 and the destination register with this add, and then also register following add. The problem is that in order to support these data dependencies, you need to use data forwarding. Also, you need to use the hazard detection unit. But vector type data, like in a single vector, we can find many elements like E0, E1, E2, blah blah blah. In the vector type instructions, we cannot find any dependencies between elements inside of a vector, right? So, which means if this add instruction, this add engine executes the add instruction for element 1, then actually this result is independent from independent on the next add instruction. Okay, we can just execute the add instruction every cycle. Then there are no dependencies between these elements. That is the benefit of vector type instructions. So, which means controls are very simple. So, the vector processor, the instructions are executed like this. The first instruction is load, then the second add, multiply, and store instruction. The load instruction executes the first element of the vector register. And then the second clock, the load instruction executes the other element, element number 1 of the vector, in the vector. But the same clock, and engine can execute the first element of a vector. So this is the vector processor. Okay. And then so there are some different types of processor, like the array processor. The array processor means that actually the array processor has the multiple processing engines. So which means that in the array processors, when the load instruction is executed, then array processor has the same number of load execution engines. The number of these engines are same to the number of elements in a vector. Okay, which means that at the same time, multiple execution engines execute multiple data operation concurrently at the same time. And then next clock, so there are also 4 different add engines, and the add engines execute the 4 different add operations. This is the array processor. So we can say that the performance of array processor is better than the performance of vector processor, but no, in a vector processor we just use the only one execution engine, but with the array processor we need to invest multiple execution engine. Okay, and so as you can see, is processors execute the vector type instructions and those vector and method. Okay, and then so we discussed how the vector type instructions are implemented in SIMD processors. And then GPU, the architecture of GPU is similar to the array processor, not vector processor. So which means that GPUs have multiple execution engines, and then these multiple execution engines execute the operations of different elements, vector type data. Okay, so this architecture of the GPU is similar to the architecture of array processor. Okay, so actually I already explained about the architecture of vector processor like this. So there is single operation engine, and the operation engine receives the elements of vector data with the pipelining, and then sequentially the results are generated. So advantage. So actually we sometimes we call some other array processors also a vector processor, because array processors also support the vector type instructions. The advantage means that is with a single instruction, then single instruction executes the multiple data. Okay, so with this architecture, then we can increase the number of amount of data, executed by a processor. So which means that we can increase the throughput. And then, so I also explained that inside of a vector, elements are independent. So which means that we don't need to consider about the data dependencies between multiple elements inside of a vector. So which means that we don't need to consider about some complex architectures such as the data forwarding, hazard detection. They also don't need to control think about the control hazard, because vector type processors do not support control instructions usually. Okay. So this process engine, the architecture do not consider about the control hazard. So the hazard and the control hazard are main performance bottleneck of processor, right? So why did I explain about the basic architecture, not basic, it's not very complex architecture, but why did I explain about the advanced architecture of CPU, and then why do we need to use this advanced architecture? Reduce wasted clocks by data hazard and control hazard, right? That's why we have developed the very complex architectures like out-of-order processing and speculative execution. But vector processors, the vector instructions guarantee that different elements in the same vector are independent. So vector processors do not need to consider about these wasted clocks by the hazard and control hazard, which means all process architectures can become simpler. Okay. Function is a deeply pipeline. It's a vector type processor and then clock that every timing. Because architecture is very it's simple, then also we can implement the hardware with the lower resource, with lower hardware resources, and also increase the clock frequencies. Its advantage. So actually, vector processors or array processors only can support the vector type instructions. Okay, only vector type instructions, like vector type instructions have multiple elements inside of a vector. So actually, this type of architecture can be applied to a specific type of applications or a specific type of data, not every type. So CPU, something like CPU. With the CPU can also support the vector type operation, right? Because we frequently use array data. Then we frequently run applications that handle array data with CPU. So actually, CPUs can run every type of applications. But with a vector processor, vector processors just support the vector type data. Other type of data like scalar data, maybe if executed by vector processors, but it is not efficient because vector processors do not support data forwarding, hazard detection, or control hazard detection. this automatically only a specific type of data can be executed by data processors. And then compilers need to find some part of code which can be transferred, which can be converted to the vector type data. Okay. So actually, class of specific vector type processor can support only a certain class of applications. Okay. And which means GPUs. So I said the GPU is the coprocessor, which means that also I also mentioned that the GPU architecture is very similar to this array processor architecture. Which means GPUs can also execute a certain type of applications. Okay. Okay. So because I did not post this slide, so we will take a 10-minute break, which is somewhat early. But during this break, I will upload the slide deck, the blackboard. Okay, sorry about that. So let's take a 10-minute break. So it's available already. Okay. So now, I will briefly explain about the GPU architecture. So first, let's think about the early generation of GPU, which is GeForce 680, 100. Okay. So I said that the GPUs are developed for graphics application, but actually the GPUs can execute the instructions developed for graphics applications actually. So GPUs already have the programmability because GPUs can execute the graphics related instructions, and parallelisms are also implemented inside of GPU. So if you took the image processing related course computer vision, and you can find that actually, so we need to generate the many pixels by the image processing application. And then these are actually the matrix operations. So the matrix includes many elements, then which means that we need actually for this matrix multiplication, the many elements can be operated and performed in parallel. So which means that, so think like the matrix multiplication. So how do we perform matrix multiplication? We just performs the row to column vector multiplication. So actually this is row to column dot multiplication. So actually we just perform the multiplication for every element of the row of the vector, and then also the column of the vector, and then accumulate the partial product of the dot product. So we can find many parallel operations in image processing application, like graphics applications. So already the GPUs exclude the data parallelism, okay, and then memory. So how can we design the memory hierarchy of a GPU? Also, let's think about how we can implement the memory hierarchy of a CPU. In a CPU, so what is important? The memory hierarchy. If we just consider the memory hierarchy of a CPU, then what is important? It's latency, right? So why do we use the memory hierarchy? register 5, this is around cache, inside 2, and the memory. So why do we use memory hierarchy? Because we want to reduce latency for load instruction. So that's why we use the memory hierarchy inside of the CPU. But the GPU supports the data parallelism, which means actually many data, lots of data can be executed in parallel in GPU. Then, GPU memory, then we need to consider the also bandwidth, right? So think like this. Oh, this is the GPU, and then actually GPU, the NVIDIA advertised that GPUs have 10K core, and then these 10K cores are executed concurrently. Then let us split this 10K of address cores, just execute the load instruction. Okay, there are many load instructions from GPU. So what is important? Bandwidth is important. So that's why the GPU memory supports high bandwidth. Also, the latency is also important because the latency is very critical for the performance of it as well. But the GPU architecture bandwidth is also very critical. Okay. So considering this feature, this is the architecture of NVIDIA GeForce 6800. So actually, the early GPUs supports the graphics pipelining only. So it supports only graphics instructions or graphics pipeline. But in order to support the graphics application efficiently, GPUs have already a parallel processor architecture here. Also, as you can see, the memories are partitioned. Okay, you can find many memory partitions here, and then each partition is connected to DRAM, independent DRAM. So what is the benefit of this architecture? So each memory partition is connected to DRAM chips, so which means that there are multiple channels that can access multiple DRAM, which means we can increase the bandwidth. We can increase the bandwidth to DRAM. So as I mentioned, the GPUs requires high bandwidth from main memory to GPU device memory. So that's why the GPU memory have that like this. Also, as you can see, you can find many execution engines here, and then the execution engines can parallelly execute graphics instruction. So when the GPU has the exchange, so some specific graphics processing engine, GPU has the multiple exchange. So this is our architecture of early GPU. Okay, but as you know, as you can see, the early GPU architecture also considers these features of programmability and then parallelism, high bandwidth memory. Okay. So this is actually also I need to add some branch instructions like the actually I already said that the GPU supports the programmable based on graphics instruction, but in order to support the strong data parallelism, so which means it's the same to the vector processor actually. It's the same to the architecture of the other processor or vector processor. So in order to support the strong data parallelism, and GPUs need to support the independent processing. So concurrent execution for many data. Okay. So GPUs actually does not support the control flows. Well, it can support the very basic control flows, but GPUs cannot support. So GPUs does not support control flow. Actually, it's for the early GPU, GPUs just does not support the control flows. So think like the ASIC, some ASIC design. So when we design a domain-specific chip or it's AC, so we do not consider about the control path of the ASIC design. The ASIC just supports the defined execution path, and that's it. It's also same to the GPU. GPUs are developed for rapid instructions, so that then actually for the efficient parallel processing, GPUs do not support control instruction. But recently, the GPU is the general purpose GPU, so it means that GPU code also needs to support branch instruction. Okay, it's the core of the instruction, right? When we write the code, we frequently use the for loop, and then if then else. We use this statement very frequently. While loop also. And then in order to support the data operation, then GPUs need to support control instruction. And then that's true for the modern GPUs, but as you can see, original GPU is designed for supporting these features. So programmability, so simple programmability and data parallelism and high bandwidth memory. So considerations for control instructions are very low. It's not considered. So, which means if we use the control instructions in GPU, modern GPU architecture, even though the modern GPUs support control instructions like the performance will be low. Okay. GPU. So the recent modern GPU is the GPU. The first GP means general purpose, okay, and graphics processing. The second GP is the graphics processing, but the first GP is the general purpose. So general purpose GPU means that it's just GPU. So we use GPUs for game applications, image processing, video application. It's true. But plus, GPU also supports the general programmability. And then, in order to support the general programmability, NVIDIA or AMD supports the program framework called the CUDA. It's supported by NVIDIA and OpenCL. OpenCL is supported by AMD. And then, by using CUDA or OpenCL framework, you can write many general codes such as the graphic processing, neural network, and data analytics. Actually, these applications are handled by CPUs, but recently, GPUs are widely used for processing many data, large data, actually, the big data. Okay, so as you can see, if you see that this type of application, you can find what graphic processing, and then graphic type large graphic type data. Okay, neural networks, the neural networks also handle the large data, so the neural networks also includes a very large amount of matrix operations, and the data analytics. So like the database or data analytics, we can also use the GPU. So what is the features of these applications? Actually, we do not run operating system with the GPU, right? But then, what are the features of this type of data? The first, it's big data. It's called the big data, but actually big data, which means it's a large amount of data. Then the second feature is the parallel processing. Okay. So actually, the GPUs are deployed for large amount of data, and which can be handled by parallel processing. That's why GPUs are co-processors. Okay, it's a domain-specific processors, right? Then, as I mentioned, in order to support the programming of GPU, NVIDIA supports the CUDA, then AMD supports OpenCL. So, but recently, we use CUDA frequently because actually OpenCL is developed for the heterogeneous computing, general heterogeneous computing, and then the OpenCL also, in the OpenCL you can also write the GPU code, but recently the CUDA is more famous, so it's more popular. So actually we frequently use CUDA, okay, CUDA C. So actually in this class also we will cover the basic CUDA framework, the basic CUDA program environment. Okay. I'll skip here. Okay. So let's see the GPU architecture. So think like the general purpose application, then how these general purpose instructions are executed in a general purpose processor. So general purpose processor instead, it's CPU, right? So CPU can execute any types of application. So which steps are required not to execute the instructions? Then we require 5 steps: the instruction fetch, ID, execution, memory, write back. So we learn these 5 steps in the undergraduate computer architecture course. So actually, memory. So recently, the actually modern architecture, the memory is here. So which means that the execution part and the memory part can be executed in parallel. But we can say that in order to execute a certain instruction, we require instruction fetch, instruction decoding, execution, and memory, and write back. So why do I explain this? It's the same to GPU. In order to support general programming with GPU, which means that GPUs need to support execution of general purpose instruction, and then actually the baseline is a fundamental steps. Fundamental required steps for executing instruction is the same: instruction fetch, instruction decoding, execution or memory, and write back. Just remember this. This is some fundamental knowledge in the computer architecture field, but these fundamental knowledges are also employed in modern architectures. Okay, not execute general purpose instruction. We need these steps. Okay, instruction fetch, instruction decoding, execution, and write back. GPUs have the same architecture, but the architecture of GPU is different from the architecture of CPU. But just remember that GPU architecture also supports these steps. So memory hierarchy. Why do I mention memory hierarchy here? To change that, GPUs also serve as memory hierarchy. I explained that why why do we require memory hierarchy? Because the latency problem. But in the CPU domain, CPU has the register file and then cache hierarchies and main memory and storage. GPU has because the GPU is a coprocessor. GPU does not have any storage part because the storage layer is managed by operating system. So the GPUs do not run operating system. Also, GPUs cannot manage storage system directly. But this activity also supports the direct storage technology. But in general, the storage part is not included in the GPU because the storage is managed by operating system. So, which means, GPU is the general purpose processor, which means GPUs also have register file. Why? Like the RISC instructions like add x1, x2, x3. So RISC type instructions, arithmetic instructions handle register operand. Okay. And then I also mentioned that GPU has register file, and then GPU supports program mobility, which means GPU instructions also. GPU instructions have the similar forms like the add R1, R2, R3. It's very similar. If you see the GPU, it is different. The GPU ISA, like the NVIDIA PTX ISA, is actually different from the GPU ISA, the RISC ISA. But the basic structure of ISA is the same. Okay. GPU also execute the add R1, R2, R3. So which means GPU has the register file. Okay. Also, cache hierarchy. In the CPU domain, CPU has the L1, L2, L3 caches usually. So actually, L1 and L2 are private cache. L3 is the shared cache. Then, why do we use cache hierarchy? Because the processor handles the small memory and it's fast. As you can see, if a processor handles large memory, it's slow. That's why we use cache hierarchy. Then in the CPU architecture, L1 and L2 are private caches, and the L3 is the shared cache. GPU. Actually, the original GPU, like GeForce 680-100, does not have any caches because it supports some general graphics instructions, but actually, in order to handle some graphics data is stored in the on-chip memory called the scratchpad memory. So scratchpad memory means what is the difference from scratchpad memory and cache memory? So the scratchpad memory, programmers need to manage data in scratchpad memory. Okay, because graphics applications actually the data movement is it's a fixed thing, which is that some part of image is buffered in the scratchpad memory and the GPU, and then only this part is used for the processing, and then also the partial result are stored in another scratchpad memory, and then it is delivered to the main memory, something like that. But GPU needs to support the general application, which means that we do not know the data management or data executions data fetch or store control. Actually, it's not fixed. It is controlled by load or store instructions, but we don't know how the data can be used by instructions. So, CPU has the error cache hierarchies, but these caches are managed by hardware, right? And then also GPU. As GPU supports the general purpose applications, GPUs also now have caches. GPU has only 2 level caches, error and 2 caches. And then the GPU cache, error cache is the private cache. It's called the private cache, but the meaning of private is a little bit different from the meaning of private in GPU domain. But we can say that error cache of GPU is the private cache. And cache is the shared cache. Okay. So the main memory. CPU domain main memory is the DRAM. Also, it's it's the same as the GPU. Let's say GPU. The main memory of the GPU is the external memory. So GPU use the DRAM as the main memory, like GDDR5, GDDR6, or HBM. Okay. So it's also DRAM, but this DRAM is different from the host DRAM of the CPU. So we frequently call this DRAM is the device memory. Okay. Sometimes I call this is the device memory. So if you see some photos of the GPU card, so you can find the here. So you can find that this is a very large GPU chip, and you can find many memory chips around a GPU chip. So these memories are device memory of GPU, right? So you can find many memory chips. So what is different from the host memory? So these device memories are just stored on the GPU card. You cannot change the GPU memory, right? The CPU memory, so we just purchase CPU DIMMs, attach the more CPU DIMMs if we want to increase the capacity of the GPU memory. For the GPU, these memory chips are just soldered on the GPU card, so you cannot change the size of the GPU memory. So also another different feature of GPU memory is that. So actually, in a CPU has the multiple channels, but the memory devices can be connected to this some channels of the CPU. Also, we can use the empty slot, so which means that the memory is not connected to the CPU channels. But in the GPU, because the memories are already stored on the GPU card, so which means that GPU used actually existing memory. GPU use all existing memory channels supported by GPU chip. It's already solved. We cannot change this configuration. Okay. So it's a device memory, DRAM, so it's a DRAM. So you can find the architecture of GPU like here. So this figure shows the brief architecture of the GPU. Okay, I mean, actually, so this is the external memory, so like GPU device memory, and then GPU chip includes until this part. GPU chip includes this streaming multiprocessors and shared L2 cache memory controllers. Okay, then external the DRAMs are connected to outside the of GPU. That's why device memory is the external memory. Okay. Let's see the brief architecture of GPU. So actually, this is the GPU architecture. Sorry, actually I forgot to add the CPU architecture. So let's think about the multi-core architecture of CPU. Okay. We'll use the blank space here. So, how the multi-core architectures are assigned inside of a single CPU? How? So, if you see some diagram of Intel Xeon CPU architecture, then you can find many cores at here, and then these many cores are connected each other using interconnection network. Then modern Intel CPUs use the mesh type interconnection network. Actually, the older generation of the Intel CPUs use the ring type interconnection. So recently, they changed the interconnection network to the mesh type interconnection network. And then also actually Intel cores, this is the node, and then some nodes is the memory controller part. So memory controller is connected to the external DRAM. And then Intel also has the shared memory, shared cache. The L3 cache is the shared cache. And then these L3 caches are attached to the H node of the multi-core. And then also these L3 caches are shared by mesh type interconnection network. That's how multi-cores are designed in CPU domain. Then let's see the GPU. GPU use the different terminology. Now, actually, in a CPU domain, we use core. The core means the independent processor, actually. And then the multiple cores are connected via interconnection network. Also, these cores also share some partitions of level 3 caches. And then also via the memory controller, the CPU chip communicates with the external memory, so main memory, DRAM. This is the basic GPU architecture. What is different? What is the same? What is the similar? So we can find the interconnection network here. Then also we can find that via the interconnection network, shared caches and streaming multiprocessors called SM, because it's a streaming multiprocessors. Multiple SMs are connected via interconnection network to the shared L2 cache. Okay. This is very similar to the multi-core architecture. But we learned that GPU has the 1,000, not 100. So 100 to 1,000. So the recently it's 1,000 to 10Ks. No, something like 1,000 cores. 1,000 cores are connected. So which means that 1,000 cores are connected via interconnection network, and then these cores are also shared the cache partitions like this. So the thing like this, 1,000 cores are connected via interconnection network. Is that a proper architecture? No. So actually, I mentioned that core. Sometimes the NVIDIA. I think the NVIDIA used the incorrect terminology, but I think it's the advertising part. I said that core is just like ALU. Okay. So actually, if you see this streaming multiprocessor, and then you can find that multiple streaming multiprocessors like SM1, SM2, SMN. Actually, the streaming multiprocessor is similar to the core of a CPU domain. Core, it's very similar to the core of a Intel CPU. So then why NVIDIA advertising our GPU has 1,000 cores? It is because it is a single stream multiprocessor. Nowadays, hundreds of threads can be executed concurrently. That's why, and then use execution of 100 threads are assigned to multiple ALUs or multiple cores, the CUDA cores, SM. That's why NVIDIA is advertising, GPU has hundreds of cores, thousands of cores, and then GPU can execute thousands of concurrent threads. Okay, but core is very similar to ALU. And then actually, SM is similar to the core of CPU. So actually, all the GPU, so recent GPU has about around 32 SM, so which means that in a single GPU chip, there are 32 cores, which means that this composition of the 32 cores is the number of cores, number of SMs is similar to the number of cores of Intel Xeon CPU, right? That's why the SM, actually the SM is mapped to the cores of Intel CPU, but NVIDIA advertising that actually our GPU has many cores, thousands of cores. Okay. So actually, in a single GPU chip, there are tens of SMs, and then each SM is connected via interconnection network. And then, as I mentioned, multiple L2 cache partitions are also shared by interconnection network. And then we don't know which interconnection network is used for NVIDIA, but actually, the GPU is a simulator that we can configure the interconnection network with some different forms. So we don't know. Actually, we know that Intel uses the mesh type interconnection network, but we don't know the exact type of interconnection network of GPU. But multiple SMs and then multiple L2 partitions are shared, connected via interconnection network. Then let's see the inside of the streaming multiprocessor here. So you can find that in SM, you can find instruction fetch. This is the instruction fetch engine of GPU. So we can also find instruction fetch engine in the CPU domain. So which means instruction fetch engine access the instruction cache of GPU. It's an error cache, error instruction cache. The instructions are fetched from error cache. Also, you can find that there's a warp scheduler and scoreboard. You can find the new terminology warp. So just and then I skip the explanation of the warp this time, but warp is similar to the actually instruction of CPU. So what does it mean? Actually, this instruction is similar to the vector type instruction. what is the vector type instruction? Like at something like at the 3. At the 3, P1, P2, P3. With a single instruction, this instruction handles the vector type data, and then multiple elements are included in a single vector data type. And then the warp scheduler, I said that this is similar to the instruction, actually, vector type instruction. Which means warp execute the same instruction, the same data. But in the same instruction, multiple data can be handled concurrently. Like very similar to SIMD. So also very similar to the vector type instruction. The warp scheduler means that vector type instructions are scheduled. And then also scoreboard is it's a score similar to the scoreboard of a CPU domain. And scoreboard checks the data hazard, like the low hazard, wall hazard, or war hazard. So the scoreboard checks the availability of instructions, okay, the CPU domain. But in a GPU domain, scoreboard checks the availability of work. Okay. But we can think like that. Oh, work is the vector type instruction. Okay. So work scheduler and scoreboard is the instruction encoding part or issue engine of CPU domain. Okay. So what is the scheduler? What is the instruction scheduler? Instruction scheduler issues some available instructions to the execution engine. Okay. And then there are 3 different types of execution engines in the GPU, so SP, SFU, and then load store unit. So actually SP is the integer floating point ALU. And then this is CUDA core actually by NVIDIA. Okay. So I said that the architecture of GPU is similar to the array processor. So which means that SP. So this is the warp, and the warp has the actually multiple thread, but it also this is the SIMD type instruction. So actually, in each data is connected to the SP core, a single SP core of GPU. So this is the SP, and then actually inside of SP is the integer type pipeline execution engine, and then also floating point type, and then it's the here. Okay, so GPU looks like this. Okay, and then actually NVIDIA core, this is the CUDA core. And then the number of core means that actually NVIDIA counts the entire entire cores, the entire CUDA cores. Then they advertise that our GPU has the thousands of cores. Okay. And the SFU is the special function unit. The special function unit just performs the special function, the square root, or sine, or cosine, tangent function. Okay. The load store unit. It's also the load store unit, the address memory unit of CPU, and then load store unit has the address generator. Also, I will explain about the callers later. So the load store unit just handles the memory data. Okay, and register file here. I mentioned GPU has also register file because GPU instructions no register front like CPU instruction. So because so GPU has the register file, but the feature of GPU is that GPU has very large register file. Why? So GPU supports the hundred of thread, okay? Thread inside of on SM. Okay, so think like this. This is the thread instruction R1, R2, R3. And it's a instruction, but these instructions actually GPU runs the in an SM. Hundreds of threads are executed, so which means that R1, R2, R3 are actually there are hundreds of threads, hundreds of instructions that access the R1, R2, R3. Okay, so which means GPU requires the very large register file inside of. Also, GPU has the local cache, like constant cache, extra cache, and shared and data cache. It's another feature of the GPU. And because the GPU supports some graphics instruction, natural graphics application, GPU has some dedicated cache for the different data space. Like a constant texture cache is used for text operation, and shared memory and data cache. Shared memory is the scratchpad memory, actually. So it means that the data in shared memory are handled by programmers. The data cache is the data cache. It's a normal data cache. So the data cache is managed by hardware. And then constant cache is just stores the parameter data, constant data. Okay. And then also, like if we see the memory part, via the interconnection network, many SMs are connected, and then each SM has the same structure. So the SM is similar to the core of the CPU domain. So that SM has the same. Actually, it's the same. It has the same structures. And then, there are multiple partitions. This is the feature of the GPU. And then via the interconnection network, the shared L2 caches are connected. The shared L2 caches are partitioned like this. And then each partition has its own memory controller. And then memory controller is connected to the external memory, so DRAM chips, actually. So this is the architecture, overall architecture of GPU. Just remember this architecture. Okay. And actually, I think I don't have time for this class, but in the next class, I will also explain about the detail. So inside of the SN, but just to remember, try to understand the overall architecture. You can use. Okay. And then let's see how the GPU execute GPU code. Okay. So this is the exam here. So we've learned that GPUs can execute thousands of threads the thousands of concurrent thread. Then, but I mentioned that GPU architecture is very similar to CD architecture. You can think, there's thousands of threads execute the independent instruction. Then, can we use CD architecture? So think like this. GPUs can execute thousands of threads concurrently. And then these thousands of threads, the codes are different. So it means that the instructions in the thousands of threads are different. And then if we just execute these different instruction streams from thousands of threads inside of CD-like architecture of GPU, that is it efficient? Absolutely not. It's not efficient. Why do you use CD architecture? Because we want to execute the vector time instruction, which means the single instruction and multiple data. CPU architecture is actually similar to the CD architecture. It's an array processor. Then how can we execute the thousands of threads? It is because the GPU code is called the kernel. Actually, this is the code which are executed by GPU. Actually, in the same kernel, GPU generate the multiple thread. Okay. So which means that this is the kernel of the GPU. So I will execute this part of the GPU, but when the kernel is launched on GPU, this kernel generates the thousands of threads. What does that mean? Actually, thousands of threads share the same code. Thousands of threads execute the same instructions. Okay. So this model is called the single kernel multiple thread, SKMT sometimes. Single kernel multiple thread. So it means that actually the multiple threads are generated from a single kernel, and then actually GPU execute these multiple threads. So I said that, then think like this. I said that GPU architecture is similar to the CMD architecture, but if every thread execute the same instruction, but even though the instruction is the same, the data handled by this instruction is different. Each CMD, same instruction, but there are multiple instructions. But multiple instructions handle the multiple data. But instruction is the same because the instructions are the same. We can merge these instructions with the single instruction, right? It's just model actually. So and it is because the GPU, the same kernel, the single kernel generates the multiple thread. So how the GPU execute these multiple threads? Because multiple threads share the same instruction, and then GPU groups multiple threads, thread number 0 thread number 0 to thread number 31. Next GPU groups these multiple threads. And if we just focus on these multiple threads, we can find that multiple thread, these threads share the same instructions. Which means, you can generate only one instruction. So then this instruction share these instructions and then the import data, the 32 elements, right? So by combining what tangible thread that share the same instruction, then so GPU just execute these grouped thread like the single type process, single type architecture, and then these groups of threads are called or work. Okay, that's why I said that work is similar to the vector type instruction. Why? Because these threads share the same instruction, so we can merge these instructions like this. These instructions have the one same instruction, right? It's a single instruction. And then, actually the data are different, just data are different. So simply the simply processor just execute the vector type instruction one by one. GPUs also execute work one by one. There are multiple blocks inside of an SM, and then actually the GPU schedule this work to the execution unit. Then how the kernels generate the multiple thread, and then the multiple threads are assigned to multiple assets. Let's see. So in the kernel generate the tangible thread. Okay, but we cannot assign these tangible thread directly into SMs. Okay, so which means that we need to group these tangible threads in the thread group. So actually, these thread groups are assigned to an SM. Okay, what does that mean actually? If you see the kernel code of the GPU, then you can find that this is the kernel definition of the GPU. Then you can find that this is the kernel name for the kernel. Then you can also find the dimensions of kernel, like the dim grid and dim block. And then so you can find the argument of kernel here. So dim grid defines the number of thread blocks. Okay, and then these thread blocks are called the CTA, the NVIDIA terminology. So cooperative thread array. So I use the NVIDIA terminology. So CTA. So when the kernel is launched, kernel generates the multiple CTAs based on this dim grid, the grid dimension. Okay, so this example shows that kernel generates the 8 CTAs. Then, using the dim block, we also each CTA generates the thread. Okay, so in the kernel declaration, so dim block decides the number of thread per CTA, and then dim grid decides the number of CTAs per kernel. Okay, so which means that if we just multiply the number of CTAs per kernel and the number of threads per CTA, then we can calculate the number of threads per kernel. Okay? So inside of a CTA also generate the multiple thread based on the dim block. Okay? And then these multiple threads are executed inside of the GPU. But when a kernel is assigned to the GPU, actually these CTAs are assigned to the SM first. So which means that first CTA 0 is assigned to the SM number 1, CTA 1 is assigned to the SM number 2, CTA 2 is assigned to the SM number 3, something like this. Okay, you can see these CTAs are assigned to multiple SM. And then inside of when the CTA is assigned, so we also know that CTA generates the multiple thread. And then we GPUs group these multiple thread to work. Okay. So why can we group these multiple threads to a work? Because in this figure, these threads are generated from a same kernel, right? Which means the instructions are the same. Because the kernel code is the same, only data is different. So when the kernel is compiled, then this kernel will generate the same instructions. So which is the CT generated from the same kernel also share the same instruction. Also, the work as a thread generated from a CTA also share the same kernel code. And then, as I mentioned, GPU groups the tangible thread. Actually, NVIDIA groups the storage thread, then to generate a work. And then at every clock, the SM schedule work to execution units like SP, SPU, and root state. That's how GPU works. Okay. So from the same kernel, multiple CTAs or multiple threaded blocks are generated. And then from a CTA or from a thread block, multiple threads are generated. And in the GPU architecture, CTAs are assigned to XN. It's very similar to a thread assigned to multi-core CPU, right? So multiple threads are assigned to multi-core CPU. But in the GPU, multiple CTAs, the CTAs are also generated from a single kernel. CTAs are assigned to XN, the same processor. And then inside the CTA also generate the multiple thread GPU group the multiple thread into a work. And then these multiple thread, the same work share the same instruction, which means that program counter is the same, right? So actually, these works are independently executed inside of an SM. But inside of a work, each thread share the same piece because the instructions are the same. So share the same piece. So actually, each work execute the same instruction because the piece is the same instruction. And then, but the data is different. So it's similar to the CD. So instructions are the same piece. Okay. That's how the GPU execute the GPU kernel. Then how the GPU execute the thousands of threads concurrently. Okay. Actually, the thread, thousands of threads are generated from a single kernel, which means the threads actually share the same code. Then, when these threads are executed, then the threads are grouped to work, then share the same piece, then work execute the same instruction inside of the GPU. Okay, this is the primary architecture. So if you see the primary architecture, you can find that this cores, they also lotus the unit, there's a CPU here, and then actually the warp, each thread of the warp is assigned to the each core of the P, and then SFU, and then lotus the unit. Okay, but just remember this basic execution model of GPU. So you can say that a GPU is very similar to the SIMD architecture, but now to support the SIMD architecture efficiently, the GPU generates the multiple thread from the same kernel, then GPU from the thread into work. Actually, the work will execute inside of the GPU. Okay, so this is the very basic architecture of the GPU. So I hope you can understand the architecture of GPU. So actually, in this class, I will use the NVIDIA terminology, but also the AMD is also produced. AMD also produced the AMD GPU, so we can use the AMD GPU as for the general purpose parallel processing applications. But terminology is a little bit different. Okay, so actually, just the terminology is different. So actually, the main architecture is very similar, but just the terminology is different. Okay. So in the OpenCL, actually registers. So I mentioned that the register is actually the CUDA is compiled and is compiled into some instruction like R1 and R3. So you access the registers. But in the OpenCL, this register is called the private memory. Okay? Private memory, and then the multiprocessor. So SM, streaming multiprocessor, is the compute unit in AMD terminology, it's OpenCL terminology. And then shared memory is the local memory. It's just the terminology is different. And then it's the same, the global constant data cache, global constant data cache is the same. And then warp, actually, warp is the wavefront. And OpenCL. So I just summarized the terminology of the CUDA and then OpenCL. So actually, kernel is the same. The kernel is some function or some part of the program that can be executed by GPU. CUDA also OpenCL just code its part is the kernel. And then thread block. Thread block actually. Thread block is I think the thread block is the standardized terminology. It's a correct terminology, but NVIDIA just called the thread block as the CTA. Okay, this is the NVIDIA terminology. But NVIDIA also called the thread block as CTA as the thread block. Okay. But now OpenCL, we AMD use the work group. Then thread is the work item. Okay. The global memory is the same, and shared memory is the local memory. Local memory is called the private. Just terminology is different. But we will use this terminology in this class. Okay. Okay. Then also warp is different. Warp is wave for the AMD GPU. Okay. So this is some basic architecture of the AMD GPU. The AMD GPU is a little bit different from the NVIDIA GPU, but the basic architecture is very similar. Also, the ISA is different because the GPU ISA is NVIDIA GPU just developed by NVIDIA. Also, the AMD used its own ISA for the GPU. But as you can see, you can find that every AMD GPU has the processing engine. Okay, it's similar to the training multiprocessor of the XM. Also, you can find some specification of this 32 kilobyte local memory is the shared memory, the critical memory. So sometimes the terminology are confusing, but it's actually the architecture is very similar. Okay, so actually in this class, I will use the NVIDIA terminology because the GPU the simulator also developed from the NVIDIA GPU. Then actually, in the academia field, many researchers use the NVIDIA terminology. So it's true that also AMD engineers use the AMD terminology, but the NVIDIA power is stronger than the in the GPU domain. NVIDIA's power is stronger than AMD, so that's why we frequently use NVIDIA terminology for the GPU architecture. Okay, so I start here. And then any question? In the next class, we will learn about some more detailed execution model of GPU kernels and how also we will learn how we can write some simple GPU kernel, and how the kernels are interact with the CPU domain and the GPU domain. So if you don't have any question, I will stop here. Thank you for your attention and see you in the next class. 감사합니다.